Hi there. PN Labs, a small company located in Montreal, Canada, kindly asked me to have a look at some of their products. I picked the Flex Strip, which is an electronic fuse, and the NanoBuck, a DC to DC converter. Today I'm looking at the NanoBuck and leave the Flex Strip for another video. Inside the anti-static bag is the little PCB with the NanoBuck. To my surprise, the accessories for breadboard use are in a separate sealed compartment that needs to be cut open. Possibly because PN Labs sells their modules as ready to be permanently integrated into other products, in which case you would not need any of this additional stuff, consisting of a choice of either straight or angle pin headers and a little self-adhesive heatsink. Where should the heatsink go? On the chip, like an oversized hat? Or on the back of the PCB? The manual for the NanoBuck is silent on this. I asked PN Labs and they say either location is okay. In any case, the converter is quite efficient and may not need an extra heatsink, so I will leave this off for now. So what exactly is the NanoBuck? Here's a summary of the features. The headline says it all. 4.5 to 36 volts input converted to one of 4 configurable output voltages with up to 2.3 amps output current. Apart from these basic facts, the chip on the NanoBuck uses special measures to reduce the noise produced by the switching, dual random spread spectrum and all that. The chip itself is a Texas Instruments TPSM 33625. There are 2 versions of this chip, one with a fixed base switching frequency and one, the RDNR variant, where the base frequency is configured by a resistor named RT. This latter version is the one on the NanoBuck. To reduce emissions, the chip has the controller, power MOSFETs, inductor and capacitor all integrated into the tiny QFN package. Quite amazing if you think about it. The first thing to do is to select the output voltage. For that, there are pads on the PCB. The PN Labs datasheet for the NanoBuck shows what to do. The red markings represent solder bridges or 0 ohm SMD resistors if you want to be fancy. In my case I want 5 volts, so I need to add solder bridges below the 5 volt print on the PCB. Sorry, my hand was blocking the camera, but creating the solder bridges is not a difficult job. Since I want to test it on a breadboard, next is soldering the pin headers. I selected the angled version. After soldering the first pin, I checked the alignment, which can still be tweaked at that stage. Happy with that, I can solder the rest. And reflow the first to release any stresses that the alignment may have caused. This is my test setup. Essentially, the module is just a 3-pin conventional regulator. 1 pin for the input voltage, shown yellow here, 1 pin for the output, shown red, and a shared ground connection, for which the PCB provides 2 connections. After all, we could have 2.5 amps flowing. That is really all that's needed. The other pins can be left unconnected. Out of interest, I connected a red LED to the PG or power good connection. This is an open drain. It goes low if the power is not good. Since the max current for PG is 4 mA, one needs to be a bit careful with a resistor for the LED or the input voltage. For my tests, 2.2K will do just fine. The EN or enable pin can be used to turn the converter off when pulled high. And this is the actual breadboard using the schematic I just showed. The wire colors are yellow for input, black for ground and red for output. A first test with 9 volt input and no load connected delivers 5.02 volts output with less than 1 mA current drawn from the bench power supply. Did you notice the red LED flashing briefly when I turned the power on? It's okay, let's do it again with the camera zoomed in. It's on very briefly until the output has stabilized. I will test this in more detail a bit later. Let's try loading the chip first, starting with a modest 200 mA. No problems. Moving up to 500 mA. It appears as if the voltage is sagging, but that's due to the voltage drop over the relatively thin wires. I should have measured the voltage directly on the PCB, not at the electronic load. Anyway, if I switch to AC, we get an idea of the noise produced by the chip, about 2.6 mV RMS. Of course, that needs to be taken with a grain of salt, as the highest frequency of this multimeter is about 100 kHz. A better way is using a scope, although I did use a probe with a standard ground strap instead of a special spring that one should use for this. I recently moved my lab and somehow I can't find where I put those springs. With that caveat, this here is the noise with no load, about 6 mV RMS. At 200 milliamps the noise is a bit different and actually slightly lower, 5 mV RMS. At 1 amp it's very much the same and again a touch less, about 4 mV RMS. And finally at 2 amps a different noise pattern and again 6 mV RMS. These values are quite good and should not cause any issues with most applications. Noise is one thing to worry about in a power supply, the other is heat. I pointed a thermal camera, the Topton TS001, to the NanoBuck and set the load to 1 amp. This is what the thermal camera saw. I accelerate the playback somewhat. Topton's choice of using by default a white font makes the temperature reading on the chip itself difficult, but since it's the hottest point, you can just look at the value on the top of the bar on the right. The temperature settles at about 43 degrees Celsius or 109 degrees Fahrenheit. For 1 amp current, that's pretty good. Considering drawing 1 amp at 5 volts or 5 watts, while the power supply provides 8 volts at only 672 milliamps or about 4.5 watts. This means the NanoBuck is running at 93% efficiency and has less than 0.4 watt losses. If this were a linear regulator, the same 1 amp output current would be drawn from the power supply and the regulator would have to drop 8 minus 5 equals 3 volts, dissipating 3 watts and running at only 62% efficiency instead. I ran another test using 1.5 amps load. On the Topton app I tried to record the temperature over time, but this version doesn't have this feature anymore. Instead it has plenty of AI stuff that needs payment. There is, however, a trend function, but that's a graph over the temperature on a line drawn on the screen, so a spatial plot, not a time-based. Anyway, the highest temperature is about 65 degrees on the chip. Still wondering where a heatsink could go, I decided to check the rear of the PCB as much as I could, rotating it without disconnecting any wires. About 55 degrees, so we have a 10-degree gradient between the top of the chip and the back of the PCB. This means the back could be used as a heatsink, for example by mounting it via a thermal pad directly on the inside of a metal enclosure. I decided to deinstall the 2025 version of the Topton app and replace it with the older one that I used when I reviewed the camera. This has a super useful temperature monitoring function and allows saving the data into an Excel file. I rerun the previous 1.5 amp load tests while recording the temperature on the chip. At about 25 minutes, I lowered the current back down to 200 milliamps and let things cool down. The exported Excel spreadsheet as a graph. It confirms the chip will be running at 65 degrees Celsius or 149 Fahrenheit at that load. The wiggle close to the 500 second mark happened when I accidentally knocked the thermal camera out of alignment. I have tested the 5 volt setting and I have no doubt that the other 3 settings would work very similar. But what if you need a different voltage from those 4 on offer? Can the NanoBuck still be used? I decided to reverse engineer how this thing works as far as the voltage selection goes. This involves measuring super tiny SMD resistors, not an easy job for old eyes. Here's the result. It turns out that the actual voltage selection is done with a lower row of jumpers. The 4 resistors are all connected with one end to the output voltage pin V out. If a solder bridge is set, it connects the resistor to a 10K resistor going to ground. This forms a voltage divider, providing the feedback voltage to the controller and the chip via pin FB. The datasheet of the chip calls the voltage selection resistors RFBT and RFBB. The upper row of jumpers selects the base switching frequency. The solder bridge here selects a specific value for RT. When selecting 5 volts earlier, I actually configured an RFBT of 40K and an RT of 16K. This is a snippet of the TPSM 336X5 datasheet concerning the selection of the switching frequency using RT, depending on the input voltage and the desired output voltage. I marked the RT values that are on the NanoBuck. For 5 volts, I measured 16K, which means 1000 kHz. This RT value optimizes operation for an input voltage of up to 12 volts and 1 to 6 volts as output, but it would also work for up to 24 volts input and an output between 2 and 11 volts, or an input of 36 volts and an output of 2.5 to 8 volts. Obviously, if you have a choice, you want to use a lower input voltage, as the efficiency of the chip drops if the input voltage is much higher than the output, as this graph from the NanoBuck datasheet shows. That datasheet, by the way, contains lots of nice graphs that have been done by PN Labs testing their own NanoBuck. The recommendations for the voltage selection resistor RFBT is based on using an RFBB value of 10K in the voltage divider, which is exactly what the NanoBuck does. The value of the NanoBuck for 3.3 volts, 5 volts and 12 volts are very close to the values in the table. The value of 9 volt is not in the table, but can be calculated using the formula below. So that would be 9 minus 1 equals 8 times 10K or 80K, which is exactly what I found. Let's say I want 6 volts instead of 5 volts. By the formula, that needs an RFBT of 50K. Clearly, I could jump up 5 volts and replace the 40K resistor with 50K. Alternatively, I could leave the 40K and instead of a solder bridge, I could solder a 10K resistor over the pads. RT would still be 16K, as the 1000 kHz selection would work just fine. That works for fixed voltages, but if I want to make the voltage changeable, because I need to adjust to something between 5 and 6 volts, you see, in some cases a power supply needs to be located where the heat doesn't disturb, while a circuit consuming the power at quite some current is somewhere else. For this to work, the power supply output needs to be adjusted slightly above 5 volts to ensure that 5 volts still arrive at the consumer despite the voltage drop over the connection. You can't really predict that drop accurately, so it's best to have a trimmer and adjust the output voltage by measuring what actually arrives at the consumer. I don't want to mess too much with the NanoBuck changing its resistors. Therefore, my plan is to remove the solder bridge on the 40K and solder a trim pot across the pad for 3.3 volts. That has the lowest resistor of 24K, which will be in series with a trim pot. A 30K trim pot would be enough to allow adjustments from 3.3 volts to 5.4 volts, but I don't have one of those handy, so I selected a 50K pot instead. That will make the output voltage selectable between 3.3 volts and 8.4 volts. Yes, a better solution would be to solder a 10K pot across the 5 volt pads, but I did not have one handy, and this is just a test, not a final version. I may change to that configuration later. The trim pot is actually an old 10-turn type that had lost one of its legs. For this test, the third leg is not needed, so it will be just fine. Don't look too close on the soldering. I will probably replace it with a 10K pot over the 5 volt position if it works. It turns out that soldering 2 wires on one jumper pad without creating a solder bridge is hard. After all, these are designed to make solder bridges easy, so I use the right hand pad of the 5 volt position. All these right hand pads are connected together anyway. Let's try it out. After power up, I get 5.5 volts. Excellent. Let's see if I can change it to 6 volts. Sorry, since the pot is only dangling on 2 wires, I have to hold it while adjusting it, and that blocked the camera a bit, but you can see the voltage change on the meter. That worked great. Before I end, I quickly want to cover a few more things where the NanoBuck differs from linear regulators. Obviously, it handles short circuits, which are signaled by the power good signal, in this case the red LED. Notice that the short on the output is not causing a current limit as with linear regulators, but the switching turns off completely and hardly any current is still flowing, just for the controller and the red LED. Here the NanoBuck is operating hard at the limit of its input supply voltage. If I raise the current draw just a bit, the red LED comes on because while still running, it is now in a degraded state. Raising the input voltage just a bit and the red LED goes out again. I mentioned that you can see the red LED briefly when turning the power on. Here is what's really going on. The yellow trace is the PG signal measured at the connection of the LED to the pull-up resistor. The green trace is the output voltage. Time is 1 millisecond per division. At -3 milliseconds, that is left of the trigger position in the middle, power is turned on as the yellow trace shows the forward voltage of the LED. That is, the LED is now on. 2.5 milliseconds later, the chip begins its soft start and the green output voltage starts to rise. It reaches the full value after about 3 milliseconds, but the power good signal stays low for another 2.5 milliseconds to let everything stabilize. Quite similar is the behavior after the chip was turned off using the enable pin. The red LED is on while the chip is in this state. Once the enable signal is valid, the chip ramps up the output voltage over about 3 milliseconds and 2.5 milliseconds later, power good is signaled. So far you have seen the NanoBuck powered by a stabilized bench power supply. In the real world that would not be the case. Here I am feeding it from a variable AC that has been rectified using a full bridge rectifier but not smoothed in any way. To use such a supply, you need to add a smoothing cap. In this case I used a 330 microfarad cap that happened to be lying around and I connected between the yellow input wire and ground. On the scope, the green trace is the input voltage and the yellow trace the output. While the NanoBuck is able to produce a stable output as soon as the smoothed input is just a tad larger than the output, this is only true while there is no load. As soon as the load is turned on, the capacitor discharges partially while the rectified AC is lower than the peak voltage, and this causes the input voltage to drop below the required level. For this to work at this current draw, I need to either increase the capacitor so the ripple becomes lower, or raise the AC voltage so the ripple occurs above the threshold needed for a stable output. If that is the case, the NanoBuck removes the ripple on the input completely. In this aspect, the NanoBuck behaves exactly like any linear regulator would. That's it for the NanoBuck. I like it and I will be using it. Thanks to PN Labs for sending it in. I leave a link to their site in the description of the video. They are also selling via the Electrons marketplace, which is more convenient if you are in the EU or the UK. There you pay less than £13 or €15 for one. Considering that a conventional inefficient solution with linear regulators would need a larger transformer and a larger heatsink, both costing money, and then you need to mount these somewhere, and still the generated heat may cause thermal drifts in the rest of your circuit, the NanoBuck seems to be a viable alternative. Of course, nothing is perfect. Your circuit needs to tolerate the low but present switching noise, or you may have to add additional filters. But you do gain soft start, a power good signal and an enable signal, for example to implement a sleep mode. If you like my videos, don't forget to like and subscribe and help growing this channel, and consider becoming a Patreon. The link's in the description. Thanks for watching.